Okay, so yes, I'm Charlie Laub, and I'm going to be talking to you about some recent stuff that I've been doing with the Raspberry Pi, which is quite a useful tool. Okay, so I'm a loudspeaker guy. I like to build loudspeakers, and I like to develop tools for the crossovers in loudspeakers. I embrace DSP as a tool for loudspeaker crossovers. I find it very flexible and useful to do quite a number of things that you need to do for a crossover. And you know, I see products. This is just some examples. They're from Meridian. These are DSP loudspeakers, so active loudspeakers with DSP built in for doing the crossovers. And yeah, they're fascinating. You know, you have really, this company's been doing it for a long time, since the 80s, I think, and you can do some really great things, and they make very, you know, great looking products that are sort of like Pez boxes, but they're bristling with technology. And then when you go to look at what you're getting here, you see, well, they're kind of expensive, but you are getting a lot of technology. But, you know, the DIYer looks at this and they say, I can't afford that. $80,000? Yeah, I could buy a great car for that much, but maybe not a pair of speakers. Maybe I can build it. Spend a lot less and have fun, you know. And this is kind of the college student think that just keeps going as you get older. And I'm still in that mode. So I found these speakers as a good example of something that I'm doing. I'll talk to you about. So this is wireless and DSP combined. Again, there's digital signal processing built into the speaker. This is by Dynaudio, these speakers. A lot less expensive now, $2,000 for this one and $4,500 for this tower. And they sell this little Connect box that adds the wireless connectivity. It's about CD quality sound, so very nice. So yeah, I like that. It's interesting.
Nice tweeter.
Yeah. So what about that tweeter? Can anybody see what's the catch here? Anybody? Maybe loudspeaker people? How about, here's a hint. What is that? The tweeter? It's a standard tweeter, which has a 4-inch diameter plate. So these are tiny. It's like this high. So first I was really excited, you know, wow, I get this tower speaker for $4,500, but I don't know. Here's a little Connect box, it sits on top. You know, obviously a great company, it's probably a wonderful product, but you know, don't expect to be blowing your head off. But still, you know, the concept of streaming wireless to your loudspeaker with the DSP built in there for great crossover, it really has some interesting advantages. You know, you can move past that old 1970s console stereo with the speakers next to it paradigm. People like Geddes talk about distributed subwoofers. You could place your subwoofers anywhere you want, just plug them in the wall and they get audio streamed to them. So it has some interesting possibilities. And so I want to just rewind a little and set the stage for how I got into DSP and how that's kind of really come into the mainstream before I get on to the Raspberry Pi stuff. And Analog Devices came out with this chip back in 2008 that's a DSP processing chip that also has an ADC, a couple of ADCs and DACs also on chip. And so they call it a complete single chip audio system. But you really can do some amazing things because they have this whole suite of software tools called Sigma Studio that lets you set up the routing in there and define blocks for programming. And they have a wonderful set of DSP tools. And so it's much more than just sort of some kind of computerized pro audio crossover that uses your fourth order crossover slopes, etc. And you can actually dig down to very low level programming of the transfer function for each filter. And so you can do some really less common customized type things, which I'm interested in because I like crossovers. A famous example that people are using now in spades is the mini DSP. They have a couple different basic crossover platforms. And there's also one called the free DSP. This is an open source board, and you can buy a kit basically. There's actually one in the raffle, and you just solder together some through-hole parts and you got a nice DSP system. And it uses that Sigma Studio environment versus the mini DSP's own programming environment. So back in maybe about 2010 when I started to learn about this and bought a couple of mini DSP systems, I thought, wow, this is an amazing tool, but I need something to develop the crossover with that then I can use to program a little box instead of using it like a Pro Audio crossover where you just say, okay, I want my such and such type crossover at 2000 hertz. You can actually do these low-level programming of the filters. So you can really harness the power of the system. So as an example, this is about a year and a half ago or so, 2 years ago, I built an open baffle pair of speakers. I didn't bring these today because they're kind of hard to transport, but and then I built these little boxes which were going to be at the base, but I actually ended up putting it sort of behind the speaker. And it's got some Class D amps, a power suppliers, the mini DSP, and here's an RF wireless system that I was using at the time to stream like that Dynaudio system, the CD quality, but over simple modulated radio frequency connection. And so like I said, that's what I put in the boxes. And I streamed the audio using this, they call it an AV sender. It's basically for an old analog television, you use a video channel, and it has enough bandwidth so you can stream an SPDIF bit stream. The problem is, it's barely got enough bandwidth. And so you don't get really clean signal out of there. And because it's analog, you get interference pickup. And so in the home environment, once you start going farther from the transmitter than 15 feet or so, and you got walls in between because of the 5.8 gigahertz frequency, you start to have problems. You get pops and things that come in every once in a while, and it didn't work. It was a little complicated with all the parts I had to put together. And worst of all, the mini DSP DACs that were built in there, they couldn't really drive the amps that I chose to their full output potential. So I did use that for a while, and I still have it in my home, but I started to think, I better find some better DSP solutions. And maybe it's only better for the wireless, it doesn't have those problems. So I kept looking around on the web, and finally I discovered this great web page, the title's up there, by this guy named Richard Taylor. He's a guy from Canada, and he has this amazing how-to. And what is it showing? It's showing how to use some cool Linux software to do crossovers on really small and inexpensive computers. So he used a program called EcoSound, and this is kind of like a routing software for audio processing, but it can work with real-time streams. And you take your input streams, split them into your multiple channels for your different drivers, and then you can apply processing to those, like filters or whatever. And then he combined that with something called LADSPA, which is some kind of audio plug-in specification. So it routes the audio stream out into this LADSPA plugin where you have some code that's processing the blocks of audio coming through, and you can apply your filter to there. Again, by using this transfer function formalization of the filter, you can process it, and this is just an IIR filter, so it's pretty light computationally. And like I said, it uses just Linux tools. They're free. Okay, so this.
Quick question: is he inputting data from the manufacturer's specifications, or is he testing the drivers?
Who?
The guy that.
No, he's not doing either one. He's developing a crossover. He is actually in Siegfried Linguist's O-Plug group, and he wanted to replace the ASP for the Pluto or something like that with a digital signal processing. So he figured out a way to reproduce the crossover.
The crossover's already been established, and he's.
For him, yeah. For him, he knows what the crossover functions are, and he's reproducing those in DSP. But you need to know what those are. So I mean, that's what the LADSP is, the filter. So you tell the filter what to do, and then it just does it. So, like I said, this is in Linux, and both of these are basically just running on their own, and you give them some kind of specification configuration files that are just text files, which makes it easy to edit, and easy to edit over a network connection like SSH or something like that. So at the same time, and kind of through the lead of his web page, I started to realize that with Moore's law having chugged on a few more years since I last looked at the things, there are now these small and inexpensive computers. And why is small important? Well, remember, I want to put the crossover in the speaker. So you can't have a big computer. You got to have a little thing to fit in the box so it's hidden, right? So small is important. And the first thing I looked at was this very interesting system from ASRock. This is the motherboard model or whatever. It costs about a little under $200 to get the bare bones system working. And what's interesting is it has a Bay Trail chip, and the motherboard comes with the IC on there and a passive heatsink on the IC. So you got no fan for that, so it's noiseless. And also, it has an external power supply like your laptop might have, the little brick thing, So that's no noise. So this is perfect for audio applications. And it's about this big, kind of like a big book, but still relatively small for a motherboard. And it has 8-channel onboard audio. So I thought, wow, I got 8 channels of crossover, $200. I can do all this digital signal processing. Then I found the Raspberry Pi. So what is that? The Raspberry Pi is a little computer. It's not a powerful computer, but it's a computer. It runs an operating system. You can do kind of what you do on your desktop, just at a little more simplistic scale. And it's only about $50. Okay, wow, $50. Yeah, I can have one of those in every speaker in the house. It's very inexpensive. It's tiny. Okay, it's like a pack of cigarettes in size. It uses inexpensive storage, but it has an Ethernet port, USB ports, and has HDMI video. So you can connect peripherals to it like a keyboard and a mouse. You can put a monitor on there, or you can run it headless, which a lot of people do, which means you don't have any of that connected and it's just running on its own. And that makes it perfect for a crossover. Because you want to have that embedded there. You're not going to have a monitor on your speaker, right? So you got to have it just sitting there by itself. And both of these have very low power supplies. This one is about 35 watts. The Raspberry Pi uses about a 5 to 10 watt power supply, and actually people have measured how much power it uses if you don't have any of those peripherals connected, and it's like less than a watt. So you can have this thing on all the time. It's like a dim light bulb at best, and it's doing all the things you need. So like I said, you can have it always on, and the price is right for DIY for sure. Okay, but we got this great computer, but how can we make it work for us? We've got some problems. Okay, the first roadblock was it doesn't have an audio input, right? We're trying to make a crossover here. It's got to get the audio in somehow to get it out. So I thought about this, I was a little worried. It seemed like kind of a problem, but then I realized it's not your hardware DSP. It's not like the mini DSP, for instance. This is not meant to be another stereo component. It's a computer. What do you do with a computer? Surf the web, emails. Oh, that's right, it has internet connectivity. So you can just stream the audio over your home local area network. And you can do that from an Ethernet jack, has an Ethernet port, or you can get a cheap little Wi-Fi dongle, $10, $15, and you can stream it wirelessly. Well, oh yeah, that's what I'm trying to do, right? Wireless speaker. So it's actually perfect. You don't need an audio input jack because you're not going to be using this like a stereo component. So again, good stuff, huh? You get a little Wi-Fi dongle for cheap, and now you got a wireless computer that you can put in your speaker. Oop, problem number 2. You can get the audio in, but there's really no good audio coming out. It has a built-in little 10-bit thing. It's really bad, actually. So I had to start looking into ways to do that, and people do use the I2S bus on there, and they have some nice DACs for that, but you're kind of limited to 2 channels. So it turns out a really good solution is these USB DACs. They are cheap, There are some that will do higher bit rates, but for instance, there's an interesting combination of this chip by TI and ESS Sound, I think, makes this ES923 DAC, which is pretty well thought of. And the nice thing is the output voltage is over 2 volts RMS. Now I can drive all my amps without any problems with headroom, or at least as much as I had before. And you can find cards and products that combine these two things that are super cheap for a DAC. 35 bucks on eBay. It can go down to $15 and get one of these things for a 2-channel DAC. And it's pretty good. Even better, you can use multiple ones because there's multiple USB ports, right? So if you want more than 2 channels in your crossover, you just buy another one of the cheap DACs and connect it, and now you got 4 channels. Or I've tested up to 4. I haven't tested more, but it's really only limited by the bus throughput. And if you're not doing really high sample rates, then you're probably fine, I would assume. So again, great, problem solved. What else is a problem? Ooh, scary, Dolly. He's got problems with his clocks, right? We don't want problems with our clocks, and here's why. Now you probably know buffering is used in computer audio. You know, like if you have things coming over Wi-Fi, it's coming in packets. You gotta stream over independently, maybe out of order, and then you get to your computer and it puts everything back together in a buffer in order, hopefully, and then finally starts pulling stuff out at the other end. Okay, and so with streaming audio, the source puts little timestamps in there every few frames that tells you when the audio is supposed to be rendered out through the DAC, for instance. And we got multiple clients. Like I said, now we got this nice cheap platform. We can put one in every speaker in the house. And so the clocks in each of those might not be close. They might be a couple milliseconds off. They could be a couple seconds off. And the problem is with the timestamp that's fixed, that's going out to all of them, if you have the clocks in your clients, these Raspberry Pis, that aren't right, the audio is going to be coming out at different times, and you're going to get some really weird stuff coming out. So what happens is that very low delays or latencies between channels. First, instead of a nice stereo image, you notice it's all coming from one speaker. That's when you got sort of a timing error around a millisecond or so, 2 milliseconds. Once you get up to, say, 20 milliseconds, you actually start to hear echo, and it's weird, like some kind of strange synthetic stereo effect. And if you go even higher, you really get something that you can't even stand to listen to. So this is really important. You need to get all the clocks on the little computers in your system exactly on the right time, below some threshold, which is about a millisecond or 500 microseconds, so that the audio is basically coming out as if they're all connected with a hard cable. So it turns out Linux has this thing called Network Time Protocol, which does exactly that. It sends a little request out through the web or to some time server that you set and says, hey, what time is it? And they say, okay, this is the time. And then it does this again. What time is it? It sends back the time, and it does this periodically, queries this time server, and then it has a way to actually adjust the frequency of the local clock so that it pulls it back onto some particular time reference, the one it's been getting from the time server it's queried. And this works pretty good. And so it turns out that you can use an NTP, which is a standard Linux program or whatever, to pull all the systems in your audio network onto the same time base. So problem solved. Okay, we got the hardware, we got things on the same time, but now we need to get access to all the filters that you need. Since I'm the crossover kind of guy, right? I know of this sort of suite of filters that I want to be able to pick from to be able to design my crossover. And I didn't find those in existing plugins, are called, for LASBA, so I decided I'd write my own. So I just wrote some C code, and I've created 3 different things. One is just a basic set of filters, basically all the first and second order filters you could ever dream of. And you usually just cascade these into chains to make higher order filters and do other stuff. And that includes EQ. I also created a digital delay plugin that's a fractional delay because I wasn't happy with these kind of bucket brigade delay things, because they oftentimes with very low delays, you're actually getting down to even less than one sample, or in some couple samples range. And so if you round to the nearest sample, the error you're introducing is huge in terms of phase, and you got to keep the phase under control with your crossover. So this was a way to address that. And I designed this housekeeping plugin, and I realized just how flexible this LADSPA thing can be. So you can process audio, bring in the audio stream, calculate the transfer function on it, and send it out just like crossover. But you can do whatever you want because you're writing the code yourself. So one thing I found is I could write code that looked at the audio stream coming in, and it said, what's the level of the audio? So even if you're getting some, say, background sort of almost like static or something coming through, it's going to be below some threshold. And you can just keep looking at the audio, and when there's no longer audio, you can send a signal out to some cheap DAC or through a GPIO pin on the Raspberry Pi to trigger a relay. And what can you do with that? Well, you can have it wait for audio to show up, and then you can turn on your amplifiers and unmute the audio. And then when audio stops coming, you can wait 30 seconds or whatever you want to program, and then it can shut the amp down and mute the relay again for the audio. You can you can engage a soft start on your power supply if you got a massive transformer or other thing that needs that. You can pretty much do anything. Blink some LEDs if you think that's fun. And so it's really one of the powerful uses of LADSPA, not only just for filtering, but for doing whatever you need. Okay.
Could you gate with that?
Sorry?
Could you gate with that?
Gate what?
Gate the noise floor. So let's say you've got a noise
Well,
floor you can't get rid of. Could you use it as a gate?
Yeah, you could. I guess you could. You could do something like that. Just wait for the level to drop to some threshold and then mute. Yeah, you could do that. Okay, so we have the plugins. We can do all the filters we want, but you got to be able to design the crossover with the filters that you have, so that the loudspeaker is producing good sound, a coherent sound front, etc. And you can't just do that by looking at the manufacturer data sheet and saying, okay, I'll throw a 2 kilohertz crossover here and a 300 hertz crossover there, and that's within the passband of the driver, so everything will be fine. You got to look at the phase, you got to look at the amplitudes and match everything, and that's getting into crossover design, which I'm not going to talk about today. But you definitely need some kind of tools to do that. So I had already designed these active crossover tools for the mini DSP, and so I found that I could start with that and modify them for these LADSPA filters, and keep the same kind of measurement basis that I had for there, and for doing that. And then I could add in a couple new things like multi-axis modeling and a way to automatically figure out the delay between drivers at the measurement point, et cetera. It's just more crossover stuff. You don't have to worry about it. That's time for another talk. So I thought I'd just step you through some of those to show you what's interesting. So you can look at your loudspeaker response, and you can get it nice and flat and all that stuff. But if you want to look at what's going on in multiple axes, it helps you identify problems with the loudspeaker and maybe how you can fix them. And if you can do that while you're designing the crossover with a good model of the loudspeaker, then you can see how the crossover is actually helping to get the system integrated together. So that's what this does. The model is actually of the crossover included, and so you can see what the effects are, and you can start changing all the crossover parameters to see what's happening. And oftentimes you see it as a line plot like this. You have the on-axis response and then some off-axis responses also, and you sort of look for problems. But you can also do things like, you can look, instead of as a function of frequency, you can look as a function of angle what's happening. And then you get something called the polar plot. And so this would basically be the loudspeaker here, and sort of what's the sound pressure level as a function of the angles away from the direct axis angle. And you can find, you get some weird looking stuff, and how the response gets focused, usually at higher frequencies, into a narrow plume or band. And these are good. You know, you can look at all these different frequencies, and you can use the line plot to figure out where you want to look. But you can also look at all of the angles and all of the frequencies at the same time. And it is a more complicated plot, but you can see some really interesting things that you couldn't really see very easily on the other things. So the other type of plots. One of those, I'll show you here, a highlight here. You can see this kind of green band in there. And you notice that the green color is the same vertically. So what this is telling you is if you just apply some EQ there, and this is angle here on the y-axis, and frequency is on the bottom axis. So if you apply some EQ at this frequency, you can see that you can fill all this in equally, so it'll be sort of the orange color that you want. So that tells you can just stick an EQ band or two in there with your DSP. And this is why I like to have DSP, to have a lot of flexibility with doing things like EQing. But if you have a region like this, you can see there's this little green band in the middle, and then on the side are darker ones. And what that means is, off axis, you've got some beaming happening, but on axis, you actually have almost a little null forming. And if you try to put EQ here, if you just looked at your on-axis response and you decide, oh, there's a dip here, I'll just EQ it. What you're actually doing is starting to really blast a lot of off-axis sound. And you may not even realize it, but your loudspeaker may sound a little bright in the room because now you're around 2 kilohertz, and you're going to have a lot more of that reflecting back into the listening space from the room. So plotting things like this is very important.
Does that kind of plot have a name?
They call it a heat map usually,
Heat map?
or a sonogram.
Oh, okay.
And there's ways to do this in measurement packages. So you could take your loudspeaker, and you could make all the measurements, and then in the measurement package that you're using to take the measurements, you can plot this up. But then what you couldn't do is make a change to the crossover and see the effect. You'd have to re-measure everything. So the way this works is you make all these measurements first, separately for each driver, and then you sort of take some measurements that let you figure out the timing between drivers at the listening position, which has to do with the phase and how they arrive as a sound front. And then you're able to see how this plot and all these other plots that I showed you change as you start to apply the crossover and adjust all the different filters and everything on that. So it's a way to sort of do all your measurements up front and then use those to design everything well after that.
Your model covers both phase and amplitude,
Correct.
addition, off-axis as well as on-axis?
Yeah, so basically what you're doing on every axis, because you never know what's going on. So let's take on axis. So you have a tweeter, you have your mid-range and your woofer, let's say, and because of the shape of the cone and the size, the acoustic center of that is at a different location for each one. So even if the wavefront's launched at the same time, they're going to reach the microphone and they're going to be having a different phase, right? So you can establish where those are. Basically, I do it by the time. Some people do it by coordinates in space. I just do it by the time. So depending on where those are in the baffle and how far back they are and other factors, as you move off axis, those relationships can change slightly. But you can establish all of those.
Model of the speaker, you incorporate those off-axis shifts.
Correct, yes, on every axis. So it's all measurement based and all backed up by measurements, not extrapolated or with some assumptions. Yeah, so you really get a very good picture, and it's people have emailed me and said, wow, I used your program and it's pretty scary. I put the crossover in and I remeasured and it was exactly the same. So yeah, it's a great way to do it. So let's just recap about, remember again, the whole basis for this stuff that I worked through was to develop this wireless DSP loudspeaker, right? So I told you about this different software, this active crossover designer now that works with LADSPA, and the software running on the Raspberry Pis include, I use the VLC player for receiving the streaming audio and for playing things. I use this FFmpeg for doing some sample rate conversions and other things. And EcoSound and LADSPA, that's actually doing the crossover. And the NTP daemon is what's getting all the clocks synchronized. And again, you have this nice, inexpensive hardware that luckily audio processing is when you use IIR filters, it's easily handled by these. I can run a two-way crossover on the Raspberry Pi, and it's using 5% of the, on the Raspberry Pi 2 is using 5% of the CPU power or whatever. So it's lots of room to do more complicated crossovers for sure. And then you have your home local area network, which pretty much everybody has. And if you don't have one, I just went out and I bought a $20 router and I set up my own little network just for the speakers, apart from my regular home network. So you can put that into place at almost no cost. It's very easy. And so basically, you just got to add some loudspeaker drivers and mix it up a little. But actually, that's kind of a joke because how you stir, I think, is a whole nother presentation on crossover design, which we don't have time for today, but I'll bore you with that some other time. So, so basically, I've tried to sum up what I've been working on to get this streaming audio loudspeaker platform working, and I've sort of reviewed that, but there's still new heights to take this to, I guess. So right now I'm using MP3, 320 kilobyte bit rate, which isn't bad. I find it quite acceptable, actually. But I'd like to try using FLAC. Unfortunately, to do that, I have to compile my own sources for VLC, and that's just a headache I haven't tackled yet.
One shortcut may be there's a Czech internet radio station that uses FLAC streaming. So
Yeah. I can receive FLAC, no problem. But then to send it over my streaming network to multiple clients, I have to go through my special systems, and that isn't FLAC ready yet.
Probably ask them how they did it, right?
Yeah. I haven't looked into it enough to really know where the big bumps in the road are yet, but that's something I want to try. And also, I'd like to try 96K sample rate, streaming that, and I'm pretty convinced that I'm going to have to go to 802.11 AC wireless to do that. That has a lot more bandwidth, maybe at least 10 times more than 802.11n, for instance. It's just a matter of replacing the hardware with some other one. And finally, I've been talking about Raspberry Pis and all the speakers all over. I like to build speakers, so I do have quite a few systems. And when I start having multiple loudspeaker systems, and each system has multiple Raspberry Pis, I need a way to sort of turn each one on and off and direct the audio to which one I want to go to. Because remember, they're always going to be on. So I need to be able to say, I want to play my bedroom system or my living room system, etc. And so I have to come up with that. Hardware, well, I talked about the Raspberry Pi being cheap, $50. There's actually this incredibly cheap, as cheap as $15 each computer. It's kind of a clone, but it actually uses completely different system on a chip processor. It's called the Orange Pi. And I bought one to try, and it's not quite ready for prime time, meaning that the operating system ports to it are really kind of poor. But they have joined the Linux Foundation or something, so that will be just, I think, coming along the pipeline in the next year. And it just would reduce the cost threshold of this and actually give you a little more processing power. And finally, for instance, I control the volume from the player on my music server, and it has to make it through some hops and processing steps. Each one has a little buffer in it. And so I get about a second of latency. When I turn the volume down, it finally turns down after a second. So I'd like to try to work on that, but it's really not a major problem at all. You just kind of get used to it. So that's it. I'd like to thank everybody for listening today, and I hope I've sparked some interest in this very interesting, for me, platform to work with and doing digital signal processing and other stuff on the Raspberry Pi. It really is pretty cool to be able to have a little tiny computer that's capable of doing these things for $50. I think that's amazing, because when I grew up, there was an Atari 8080 or something like that, and that was about as sophisticated as you had at the time. So I'd also like to thank Antarana and Stuart, if he's around. Thank you so much for hosting us. Can't say that enough. And also for Mark for bringing together all this various crazy people and helping us enjoy quite an interesting day. So thank you. And And that's it. Are there any more questions? Yeah.
How do we follow on your work?
I do have a website, audio.claub.net. And I haven't posted this stuff up. The LADSPA plugins are posted. The crossover designer is posted. All the details that I went through here today aren't really posted yet, but I'm hoping to do a write-up with all those once they're more firmed up and everything, and I can.
Your crossover designer, what platform does that run on?
It uses either OpenOffice Calc or Microsoft Excel.
Oh,
Yeah.
it lives within Excel. Okay.
Yeah, it's actually, so Excel is pretty amazing. You can do all sorts of, so with audio, you need to keep track of phase, so you're often expressing the signal as a complex number. Excel can do that really well. And I started playing around with that back, like I said, in 2010. I just wanted to experiment with what complex numbers looked like and plotting things, and it just kept going, and it ended up just being this thing that just grew. Well, you make measurements. You get a calibrated microphone. That's maybe $50.
You can bring in a text file.
Right. Yeah. It's just a text file of frequency, amplitude, and phase, and you import that and you process it. There's a manual. You can look through that if you want.
Okay, great.
Yeah. I could post this on my website. I'd be happy if anybody else wants to host it to. Okay, maybe you want to talk to me about that. Anybody else? Yes.
Did you do any pros and cons assessments on the various Linux objects that you have? Echosound versus JAG, PLC versus...
Yeah, I actually tried, so there are a couple limitations to Ecosound. One of them is it only seems to be able to handle an audio stream if you tell it what sample rate it's at. It will not auto-detect that. So I transcode all my stuff down to one sample rate and then just live with that. And since my DACs can only handle up to 48 kilohertz, that's what I use. I tried to look into SOCs, and there was one other one that could handle these LADSPA plugins. And there are some other plugin architectures other than LADSPA. And after looking into them, I found that the Ecosound routing of the signal, how you can sort of split the input signal into different channels and then apply filters onto them, was so much easier than any other system. Some people even try to do it in ALSA natively, and they say, look, I made this crossover, I made 1 or 2 filters or whatever, I work with 20 filters. Right. And it just, I didn't see that they could extend it. I mean, they needed 100 lines of ALSA commands to do a few simple things. Yeah, so Ecosound just makes it really simple to do, and it's pretty powerful, and as long as you can live with that one limitation of a fixed sample rate, which you could always just set to whatever sample rate you want your DACs to be spitting out, and then move everything to that sample rate ahead of that, you're fine.
Your systems are running stereo to the processor and to the speakers, right? You're not using one wireless to the left and another wireless to the right?
Yes, I am. There's one Raspberry Pi in each loudspeaker. Is that what your question was?
Yeah.
Right. Because you can also have one Raspberry Pi for the system, stream to that, and then connect the speakers.
That's why the timing accuracy is so great.
Exactly. Because you're having 2 systems, one on the left and one on the right, and if they get out of whack, you hear some weird things. Okay, that's it, I guess. So thank you very much again.
What was your website again? I couldn't hear what you said. Your
Audio.